special lecture. So every semester at the Newton Institute, one of the participants is designated as the Rothschild Distinguished Fellow, and this semester, during for the semester on systemic risk, the Rothschild Distinguished Fellow of our semester is Professor Hans Follmer, who's here. And it is the tradition that the Rothschild Distinguished Fellow delivers a lecture for a broader audience, rather than just a specialized seminar for participants. And this is what's going to happen now. So Professor Follmer, most of you know him through his work. He's a well-known expert in probability theory, stochastic analysis, and mathematical finance. He has made numerous contributions to these fields, ranging from theoretical topics in stochastic analysis, interacting particle systems, and more recently he's done a lot of work on mathematical finance, the theory of risk measures, and especially he has been investigating a lot through his work on risk measures, the role of probability and uncertainty in finance. So I guess this is what he's going to talk about today.
Yeah. Thank you, Rama. Yeah, I was asked specifically to give a lecture for a general audience. Now, this audience does not look so general, so there may be a slight mismatch, but you have to bear with me. Now, too late to change it.
Anyway, so I'm the odd one out.
Ah, great, great.
So I'm the general audience.
Good. Yeah, it's of course a pleasure to be here. The first time I was in Cambridge, in the math department, or statistics department rather, was when I was a graduate student in '67. So David Williams was my host. And at that time, it would have been, I think, inconceivable to give a talk where finance appears in the title. No? So in the circle of graduate students where I was moving at the time in Göttingen, so we were starting to do probability, but in the first place we were not interested at all in applications. We were interested in basic theory of Markov processes, things like that. And if at all applications, there was a scale of respectability where, of course, mathematical physics was on top. And interesting things started to happen at the interface, mathematical physics, probability, just at that time, statistical mechanics, the probabilistic approach to phase transitions, quantum field theory. Then further down the scale, mathematical biology. Then at that time also mathematical economics. We found interesting, that was a heroic period of general equilibrium theory where a number of well-known mathematicians, also like Stephen Smale and Thom, got interested. So that was respectable. Then a long time nothing. Then in the end, maybe actuarial mathematics if we are thinking in terms of jobs. But at that time, I'm talking about the mid-60s, this was not perceived as an intellectual challenge. And mathematical finance, was not there. It was not on the radar. Like here, it has disappeared. So if one would have said finance, the reaction would have been, okay, finance, compound interest, so what, so what. Although, exactly at that time, things actually started to take off, but we in Göttingen as graduate students had no idea. No? I will come back to that. There's a situation mid-60s at MIT, for example. Let's see, how do I do this? Ah, there. Yeah, why? Something is not going. Yeah. Then some years later, I actually wrote the first paper where the word bond appeared. That was in '73. But I had a very reluctant kind of attitude to that. So in the introduction, I'm still surprised that I got away with it. I said more or less, okay, we are doing some mathematics on constrained Brownian motion. We could add some capitalistic color to the picture by phrasing it in terms of bonds. Now the reason I wrote that paper was that a student came into my office when I was an instructor at that time at Dartmouth, and asked me a question. He had been an intern for the summer at Bell Labs, and they talked to some people, including Larry Shepp, who were thinking about such applications. The student, by the way, was David Krebs, who then went on to receive the Clark Medal as the best economist under 40 a while later. Now, what? Yeah, okay. But in fact, let's go back even further. You may have noticed last year we celebrated 300 years of the publication of Ars Conjectandi. Now, if you look at Ars Conjectandi, the first three parts, the first part is an annotated edition of the treatise of Huygens. Then comes a part on combinatorics, and then a third part on application. And the application consists in using these methods to compute expected values of various gambles in the context of a well-defined game of chance. So dice, coin tossing. So in modern jargon, you could say pricing of various contingent claims in the context of a simple random walk model. And there, of course, probability is well defined as the number of favorable cases over the number of possible cases. A priori, that is clear. And Bernoulli writes, the inventors of this game have made sure that the number of favorable versus unfavorable cases are definite and well known. So we can do this kind of analysis. Yeah, sorry, it appears here somehow twice. Now then part 4, about the use and the applications of the preceding doctrine in civilian, moral and economic matters. So suddenly much wider scope. But then Bernoulli says, okay, now the question is, what is P? What is the probability? The a priori argument does not apply. In such situations where in particular human intervention takes place, it's in no way the case as before that we have an a priori knowledge of probability. So what can we do? A posteriori. No? So then we must look at similar situations, and that is his motivation then to prove the weak law of large numbers. No? So the modus empiricus, the idea is that's how we get our hands on probabilities, and then we can compute. Now there is a correspondence with Leibniz, where Leibniz in a letter in 1703 compliments him on the mathematics he is doing, his proof of the weak law of large numbers, but then raises doubts about this empirical argument. Namely, he explicitly mentions the implicit stationarity assumptions. You observe several times a situation, and then you take the empirical distribution, and now you turn around and use it as a proxy for the future to come. So that's okay if somehow the situation is stationary enough. But Leibniz explicitly questions that, which is a very modern attitude, and in particular, I also share in many situations this kind of doubt. So this agenda of part 4, the use and application of probability in economics, has of course, as you all know, seen a strong revival last century, and in particular in finance. And I find it absolutely amazing to which extent the language and the notation of mathematics, so specifically probabilistic concepts and methods, have entered and shaped the discussion in finance departments at the academic level, but also in the financial industry. And this revival was pioneered at MIT in the mid-60s, when we did not see it at all in Göttingen on our screen. There's this paper, for example, by Samuelson, Proof that properly anticipated prices fluctuate randomly. So the argument is, if you do correctly and consistently conditional expectations, predictions, then the result must be a martingale, and in that sense fluctuate randomly. So the martingale property appears in the financial context. The efficient market hypothesis, more or less the martingale property of stock market prices, and a rediscovery of the théorie de la spéculation, so the thesis of Louis Bachelier, where Brownian motion appears as a model for price fluctuation. Now, why Brownian motion? Maybe up to some transformation, for example, geometric Brownian motion, or Levy process maybe. So why this coin-tossing view of finance, title of a chapter in the book by John Cassidy, the economics editor of the New Yorker, Why Markets Fall? And you can already imagine, seeing the title of this chapter, it's not meant in a complimentary fashion. Yes. Yeah, okay. Yeah, there is one simple heuristic which says, okay, yeah, many decisions are made all the time, more or less randomly, independently, a lot of noise is going on, many coins are thrown. So Brownian motion could be expected to arise via central limit theorem, or generally some invariance principle. That's one rough heuristical justification. Now, Henri Poincaré, who wrote the report on the thesis of Bachelier, not in his report, but somewhere else in Sciences et Méthodes, has the following comment. When people get close, they do not decide randomly, and they do not decide independently one of the others. They react to each other. Multiple causes enter the picture, and they trouble people, pull them to the right and to the left. There's only one thing which remains the same, and that's the behavior of the mouton de Panurge, the sheep of Panurge, story in Rabelais, the herding effect. Et c'est cela se conserve. So Poincaré comments on the assumptions you would need to apply the central limit theorem, and one by one he questions them. Yeah, you could, since we are here in the Isaac Newton Institute, of course, recall this famous quote by Isaac Newton, that he can calculate the motions of the heavenly bodies, but not the madness of people, having first won and then lost £20,000 in the South Sea bubble as an investor. Now, if I can believe the Sunday Times a year ago, where this was mentioned, it was also translated into current value, and then the £20,000 in 1720 would amount to £3.7 million now. So that's quite amazing. Did he have this kind of money, or did he use money of the college? But it was a woman who wrote this article from, what was it, JP Morgan, so I suppose she did her homework correctly. I did not check that. Okay, another argument, the experts all know, was proposed by Louis Bachelier. Nothing in terms of central limit theorem, but a very simple axiom. The expectation, the mathematical expectation of the speculator should be zero. And that's, in more technical terms, he imposes the martingale property, so a strong form of the efficient markets hypothesis. Then, as we all know, plus continuous paths plus stationary increments implies, then by a later theorem of Paul-Lévy, that it should be a Brownian motion. Now people would not rush to impose the efficient market hypothesis in this form that objectively you see a martingale fluctuation, but there's a broad consensus that the price fluctuation of a liquid financial asset should be viewed as a stochastic process on some probability space. So many papers, especially in the 90s, started in this way. So let X be a semi-martingale on some filtered probability space. Everybody was happy. But of course, there is a considerable amount of framing going already on right now at this step, which, okay, you have uncertainty, a set of possible scenarios, for example, a path space, possible trajectories. If you just stare at one price fluctuation, information plays a role, the filtration. So what is known at any given time t, and a probability measure on the space of scenario. So in the language of Frank Knight, to which I'm coming later on, we are in the domain of risk, where a probability measure is assumed to make sense, to exist, and maybe even we know something about it. So P is the historical, the physical, the objective probability measure in this story. But of course, then if you start to think about it, you realize there is a lot of model ambiguity, model uncertainty, usually. And here is one quote by a guy you don't hear so often nowadays, but here's a quote 12 years ago, which since then, off and on, I really like to quote. Humbly speaking, our ability to forecast, even in a probabilistic sense, computing conditional expectation is limited. We have to have some humility. Okay, I will later on mention another quote which triggered the title I wrote down, admitting uncertainty, which is kind of ambivalent. Admitting is almost like admitting guilt, admitting that you have been so naive for a long time, just thinking in terms of probability and not in terms of uncertainty. But then the other meaning is admitting in the sense you admit it, you start to admit it in your conceptual and mathematical framework. So that's the message. This was triggered by a talk I heard 2 weeks ago or so by David Spiegelhalter, one of your colleagues in the psychology department, which I found very, very interesting about public understanding of notions of probability and statistics, especially in a medical context. Okay, and where uncertainty is a central issue in contrast to probability. Now, not only maybe you don't know the probability, it's often not clear that it even makes sense. And De Finetti, for example, would in many situations claim it doesn't make sense even to talk about it. So in his text on probability, page 1, the one sentence, probability does not exist as an objective thing. So that would be a very radical view. Typically, the mainstream view is somehow an objectivist interpretation and intuition. There is out there the probability mechanism. It can be identified partially by, at least by statistical econometric methods. And in the financial context, it should satisfy certain a priori constraints having to do with a more or less relaxed version of market efficiency. Well, absence of arbitrage, that's the relaxed version which is broadly accepted in the community. And then there is this basic theoretical argument all the experts know. When you exclude arbitrage, and that's defined in terms of a given probability measure P by saying, okay, if there is a strategy which produces an expected gain, positive expected gain, then there should be a positive probability of a loss. So in that sense, no free lunch. And then this is more or less equivalent, mathematically a long story, to the existence of a martingale measure P star equivalent to the underlying measure P, that is, the observed price fluctuation should behave like a martingale up to localization under that measure. So the strong form, Follmer, what I said, no, P itself, what you see is a martingale, but this is much weaker, just an equivalent measure under which it would be a martingale.
This was due to Cox and Ross, by the way. This was due to Cox and Ross.
Oh, which formulation? The the equivalence. Yeah, right. So these names should be in the list which I started with Krebs and. But then there should be Cox, and I had a number of points, and I perfectly agree. Okay, P star, not necessarily unique, usually called the risk-neutral measure, is the market's linear pricing operator. And Definetti would probably say, yeah, at that level, perfectly okay in a subjective sense, as an aggregate of subjective odds for financial bets. The market aggregates it to a pricing system, and so the subject, somehow the financial market. So if you read Definetti, he talks about you all the time to emphasize the subjective. If you replace you by the financial market, it's quite compelling reading. Here's a comment by Samuelson in this 1965 paper, why properly anticipated prices fluctuate randomly. I have not here discussed where the basic probability distributions are supposed to come from. In whose minds, as already switching to the subjective side, are they ex ante? Are they supposed to belong to the market as a whole? And what does that mean? Are they supposed to belong to the representative investor? And who is he? Are they some compromise of divergent expectation patterns? Yeah, these questions are posed at the end. They are not then further discussed, but they, of course, continue to be quite relevant. Anyway, so in the usual busyness of mathematical finance, there is not much time spent on such foundational issues, so one is happy to see this very elegant picture emerging, that no free lunch is equivalent to the fact that there are equivalent martingale measures, so the set of equivalent martingale measures is non-void, and then we know that the price process must be a semi-martingale, so it serves as a stochastic integrator, so you can do now Ito calculus on the path, and it's actually a Brownian motion. Now Brownian motion comes in if you're ready to do a possibly not very transparent random time change. That's a whole history in itself. So Brownian motion does now come in a very different route than the central limit theorem. So now we have entered the field of stochastic analysis, kind of a parallel world of great mathematical beauty and elegance, in contrast to the messy reality of financial markets, and highly efficient for special purposes, like analyzing the interplay between underlyings and derivatives, but prediction is not really one of them. And in this context, we have the paradigm of perfect replication or of super replication, and then techniques of stochastic analysis and techniques which have been developed in reaction to this application. So, for example, optional decomposition, a la Kamkov, which are of interest of a purely probabilistic point of view, independent of the application. So it has been going in both directions. For example, that's the mathematical conceptual framework for pricing and hedging of derivatives viewed as nonlinear functionals of an underlying price fluctuation. In the complete case, when there's only one equivalent martingale measure, then you prove that functionals can be written as stochastic integrals, so Ito integrals. The Ito integrals, due to the non-anticipative construction of the Ito integral, can be interpreted as a net gain from a self-financing trading strategy. And then this implies unique arbitrage-free price as the cost of that replication, which is this constant. And then if you apply the martingale measure, this expectation will be zero under some integrability conditions. And so the price can be identified as the expectation of the claim under the unique equivalent martingale measure. And so in a way, conceptually, we are back to part 3 of Ars Conjectandi, the computation of expected values of various gambles in the context of a fair game, here described by the martingale measure P star, except that the elementary combinatorial methods are enhanced by high-tech methods of stochastic analysis. But conceptually, that's what we do. So prediction in this kind of argument, in terms of the underlying P, for example, where you would worry about drift, for example, does not intervene, does not matter. You switch to the equivalent martingale measure, so you forget, you don't consider the specific structure of P as a probabilistic model of the situation. So at that stage, so that was kind of discovered by the probabilists, so in the mid-80s, and that was then the first euphoric stage where probabilists reaction was, oh, how interesting, so really non-trivial mathematics are being used. And then many well-known probabilists, some of them sitting in this audience, joined this, especially in France, Nicolas Caroui, Marc. And so this definitely raised the respectability of the field in sociological terms in the scientific community, and certainly also the attraction in the eyes of graduate students. Now, since the mid-80s, then mathematical finance emerged as a new research field within mathematics. And in particular, one must say, way before the crisis, of course, people immediately realized that this story I just showed you is too nice to be true. That in typical situations it would not be a complete situation, it would be incomplete, so you would have many equivalent martingale measures. That means the paradigm of perfect replication breaks down. Then you could think of doing some partial or efficient hedging, or and then, of course, the situation gets a little bit more messy in the sense that some economics, at least, comes in. So far, no economics, just absence of arbitrage. Because then, efficient, what does it mean? It involves preferences, so maybe expected utility. So it gets less pure in a way. So the standard setting is probabilistic. You have this underlying P, you have this pricing measure P star, which reflects in a way the markets believe. And as a mathematician, you just move freely back and forth in terms of the Gersanov transformation and don't waste too much time interpreting things. But the P, what is the P? Looking backwards, of course, you can look at empirical distributions, more or less typical patterns you have observed. You can use the empirical distribution as a proxy for the true underlying probability mechanism. But then looking forward, not so clear. Also here Leibniz question, is the situation really so stationary? And in financial markets, okay, some things maybe okay, but others, the context changes all the time. So it's not so firm as a foundation. On the other hand, looking forward, De Finetti would say, okay, probability does not exist in any objective sense, but the prices, of course, do, via financial bets based on subjective degrees of belief. So the financial market, so the P star would be all right. So as a prediction scheme, P kind of shaky, but P star much more is known thanks to derivatives, because if you look at the market's implicit prediction scheme at time t, you see a lot of that in terms of marginal distributions, which you can get from principle from prices of plain vanilla options. More complex derivatives give you some information on joint distributions. So this gives you in principle a consistent picture via arbitrage across claims and therefore also across future times, maturities, on a given day. This does not mean that the whole thing is consistent now as a whole. Tomorrow, it may shift in a non-time consistent manner, and so there may sudden shifts in the mood of the market reflected then in the P star. So something like phase transition makes perfect sense in a loose sense in this context. Now, to study the dynamics of in the space of martingale measures, that's so far not really explored. Typically, one martingale measure is fixed for an intertemporal discussion, and it would involve market microstructure. You would have to think in terms of many heterogeneous agents with interacting preferences, expectations, herding behavior. And so there is a number of toy models, but serious prediction, of course, not in sight. Now, one thing is that to think about the dynamics in the space of martingale measure provides some interesting look at bubbles. Now, bubbles, the idea is irrational exuberance versus sound fundamental. Here another quote of Greenspan. Yeah, okay, but how do we know? How do we know that it's irrational exuberance? Not so clear. But so here, there is now within this martingale formalism, one can talk about it in the following way, and that's what, for example, in a number of papers Jarrow and Protter do. Think of a cumulative dividend process and a price process. And then you take the price process together with the cumulative dividends, and that's your process X in terms of which you define the class of martingale measures. So that will be this process, cum dividends, will be a local martingale under each P star. Now each P star provides legitimate market consistent view of the future, and it supports the observed price in a speculative perspective if you think of the option to sell. That's a classical paper by Harrison and Krebs, speculative investor behavior in a stock market with heterogeneous expectations. Here the heterogeneous agents are replaced by the different martingale measures in that class P star. But there is a dichotomy. For each P star, this local martingale can be uniformly integrable or not. And depending on that, there is a bubble or not a bubble. There is either the present price is higher than the fundamentals as viewed by the martingale measure P star, then we have a bubble, or it's equal and then no bubble. And typically, in the same model, both views coexist. There will be equivalent martingale measure of one type and of the other type. There is a generic kind of example due to Delbin and Schachermayer, which clearly shows this. So, is there a bubble? It depends on the choice of the market consistent valuation P star to determine the fundamental price. It, by the way, also depends on the filtration, because the question, is it uniformly integrable or not, may depend on the filtration you're working with. And so one can now, but so far in this picture, in any case, the bubble is a non-negative supermartingale. So it cannot start in zero. It must be already there. So in this formalism, no room for the birth of a bubble. But here, as in the title of this paper, if you admit now a dynamics in the space of martingale measures, where at each time t the fundamental value is perceived by some equivalent martingale measure, and you have a flow in the space of martingale measures, then time consistency would require that you always use the same martingale measure, but which may be desirable from a normative point of view, but in real terms, I would rather follow Poincaré's comment and expect shifts, dynamics in the space of martingale measures. Now, Jarrah and Protter use a regime shift, let's say between two martingale measures of different types, then you have this kind of picture. No bubble, then suddenly there is a bubble, but it does not take off. It must be right there at the beginning. While we use a flow, also V means in this paper, this Biagini and Nedelko I mentioned, which in principle gives you such pictures. So this was an example for, among many, of how, as a probabilist, now you work in terms of the equivalent martingale measures, not in terms of the underlying P. Only the null sets of P are used, not the specific structure of P as a probabilistic model in this sort of argument. Now only, of course, is not so innocuous, because to fix the null set means to fix a lot, for example, volatility patterns. And so in recent years, there is an increasing concern about dependence on the specific choice of an underlying probability measure, even if you are only using the null sets. Now here's a quote from the Turner review on the global banking crisis. At some point, he says misplaced reliance on sophisticated math. As far as I know, then in reaction to that, British colleagues wrote a letter to Sir Turner, signed by some people in this audience, I think. And I think they actually had a meeting with him, and Turner then probably politely said, oh no, of course he respects highly and so on, but, and then he, at least in this, I don't know whether he raised it in the discussion, in the Turner report, he talks about mathematically modelable risk versus Knightian uncertainty. Now this refers to Frank Knight, his thesis Risk, Uncertainty and Profit, where he distinguished between situations of risk. Here, you probably have seen this. Rumsfeld has found a poetic formulation. The known unknowns, where you know the probability measure P, or Knightian uncertainty, the unknown unknowns, which at least means model ambiguity. So you don't have one probability measure. So a mild form of Knightian uncertainty would be you accept a whole class of plausible probabilistic models. But of course, in a stronger form, Knightian uncertainty would claim, okay, it's a situation where it doesn't even make sense to speak about probability. So in unison with definiti. But then, now I come to this talk by Spiegelhalter. Spiegelhalter on one slide in this talk, 3 weeks ago or so, in the Zengville Club in the psychology department, had one slide which says, have humility to admit uncertainty. No, that's why I used my title, Admitting Uncertainty. And then there was a very good question from the audience, a distinguished looking, I think, professor of psychology asked the following question: can we be humble and still be interesting? I mean, does it mean we simply throw the towel? Especially as probabilists, of course, this is a very touchy thing, because if we pull the rug of probability measures out from under us, what we do. No? So, yeah, as my claim is not all is lost, even if you admit uncertainty. Even more, I would say Knightian uncertainty is a very interesting and rich source of new mathematical problems. Conceptually, there are two kinds of approaches. So one is throw out probability measure altogether, just concentrate on the support, which means on a set of significant trajectories, for example, in the dynamical picture, but no probability weighting. Or you replace one probability measure P by a certain class and you work simultaneously with that class. Not in the statistical sense that you try to now, through observation or whatever, pin down within this class the right model, but just work simultaneously all the time with the whole class. Yeah, here's an example for the first variant. You throw out now the probability measure and retell the story which I mentioned in its nicest form of a perfect hedge in a strictly pathwise sense. So just one trajectory. Let's assume continuous. Not necessarily, we could admit jumps. But let's assume that it has a quadratic variation, in the sense that along a fixed sequence of partitions, which means you fix the observational scheme, these quadratic increments converge in the sense of V convergence, so you view both sides as distribution functions on measures, and on the right-hand side you have discrete measures on the real line, and they converge weakly to a limiting measure with that distribution function. Then you prove Ito's formula in the sense that the Ito integral exists now for a nice function f in C2 as a limit along of the non-anticipating Riemann sums along this sequence of partitions. And this is implied by the V convergence here at the level of the quadratic variation. And then, one step more, Ito-Tanaka formula. If the path admits a continuous local time, so the probabilistic work consists in, that's typical. For a large class of processes, you must expect that the typical path has these properties. Now you forget the typical, the null sets, just concentrate on one path which admits a continuous local time. Then the Ito integral exists for any function f whose distributional derivative is a measure, a radar measure on the real line, and you have now Ito's formula in this form. So, for example, recently Mark Davis, together with Obloy and I pronounce the name probably wrong, Pietro Sirpais, gave a talk, a very nice talk at Humboldt University a little while ago on this topic, and there is actually also a paper which Mark mentioned an hour ago, which I got, which I should absolutely also look at, by Prömel and Perkowski. Actually, I was aware of Perkowski, but not of Prömel, which also discussed the strictly pairwise construction of arguments, or reconstruction of arguments in stochastic analysis without any use of a probability measure. Now, this can then be applied to strictly pairwise hedging, to variance swaps. That was the motivation in this recent work. Also, Alexander Schied has actually lecture notes on a whole course on continuous time finance, which are absolutely probability free, including stochastic differential equations. And so this program can be pushed actually quite far. There are limits. There are limits. No? For example, the strictly pathwise construction of the Ito integral is okay up to an extent, but not for any continuous function. You can define the Ito integral pathwise as a limit of Riemann sums. That already was shown by Stricker. Only if the path has bounded variation. But that, of course, we do not want. Actually, I forgot to say, the assumption of a non-trivial quadratic variation is essential to exclude arbitrage opportunities. This you can also argue quite on a given trajectory. If it has a vanishing quadratic variation, then you can construct an arbitrage on that path. Then you can extend it to more exotic options by now really expanding the analysis via a strictly pathwise reconstruction and extension of Maillard calculus arguments. So Ramakont has been involved together with co-authors in this program, and so this really expands the scope. Now, in the same spirit, you can go back to the fundamentals, namely to the fundamental theorem of asset pricing, as it is often called, that absence of arbitrage, which was formulated in terms of a probability measure, is equivalent to the existence of an equivalent martingale measure. Here, for example, is a paper by Frank Riedel, Finance Without Probabilistic Prior Assumptions, where the probability space is replaced by a Polish space. Absence of arbitrage is just defined with some topological assumptions without probability. And then this is equivalent to the existence of a martingale measure, but now we cannot say equivalent, no P, but full support, full topological support. So that's already very nice. And there is suddenly an explosion of papers with variations on the theme. Metesona, Tusi, Bouchard, Marcel Nutz, Michael Kuppe, Samuel Drapeau, Acharyo, Schachermayer, Beigelböck, the variations of the same theme where the fundamental theorem of asset pricing is revisited in a formulation without any probability, which means no a priori P, but of course then comes up a class of martingale measures. And so this is completely consistent now with Di Finetti's view. Prices are okay, the pricing measures are okay, the probability not so clear. Now the second version is no a priori P, but you admit a whole class of probability measures which come in playing the role of stress tests. And this is illustrated by the theory of convex risk measures if you do not immediately narrow it down to the so-called law invariant case, where you would fix a probability measure, say that the risk measure applied to a function depends on the distribution of that function under the given probability measure. No, but this framework is much more general. So coherent convex risk measures were motivated by the quantification of financial risk beyond value at risk, which has the following structure. You take the smallest amount of capital, which you should add to a position X, describing the monetary outcome of your position, so it's just a real valued function on some set of scenarios. to make it acceptable. And in the case of value at risk, acceptability is defined in terms of a probability measure on scenarios, namely the probability of a loss should be bounded by a given alpha. But in fact, this has a much wider scope and many interfaces with other chapters in mathematics and also in economics. So monetary risk becomes a capital requirement in a regulatory perspective, if you like. And the general framework is, okay, you need some notion of acceptability. Value at risk is a very special case. Now, if you insist on convexity, which means that diversification should not be penalized, then by convex analysis, you get a representation which looks like this. That means you have a class of probability measures, not given a priori, they come in through the convex duality. So a class of plausible probabilistic models, let's say. For each model you compute the expected loss, you penalize with some penalty function alpha, which is actually the worst expected loss under that measure Q for acceptable positions, and then you take the worst case. So you could see this in this general form as an explicit formalization of model uncertainty, Knightian uncertainty, because you give yourself a lot of freedom here as to the class of probability measures you want to consider. None is fixed here in this general setting a priori. So it's a robust view, no probability measure P a priori, but probability measures do come in as stress tests. Now, last week, Alexander McNeil gave a very interesting talk on a more explicit connection between risk measures and actual stress testing. So that's a story in itself. This is just here a loose conceptual remark, but actually there are many interesting things going on here in connection to actual stress testing. Now, from a mathematical point of view, there is a rich prehistory, many interfaces, a special case of coherent risk measures, namely comonotonic coherent risk measures are Choquet integrals, which goes back to the 50s. Then in the context of actuarial premium principles, actually the definition of a convex risk measure without that name as a premium principle appears in work of Gerber already in the mid-80s. Then in the coherent case, the basic representation theorem appears in Peter Huber's book, Robust Statistics, just under a different name. And there is one interface which I find particularly interesting and compelling to economic preference theory. So preferences in the face of risk and uncertainty, on positions. Typically you have a numerical representation, so x is preferred to y if for some kind of utility functional it looks better, u of x is bigger than or equal to u of y. Now in the classical preference theory von Neumann, Morgenstern, Savage and so on, they formulate classical axioms of rationality which then imply that this representation takes place in the form of expected utility. So there is an implicit utility function and an implicit probability measure in your preferences if those preferences satisfy the rather rigid classical rationality axioms. Now, the whole literature, paradoxa, different stages, so more flexible axioms of rationality, for example, Gilboa, Schmeidler, and more recently, Maccheroni, Marinacci, Rustichini. And there the outcome is that under these relaxed axioms of rationality, it appears that the numerical representation takes place in this form. The expectation with respect to one probability measure is replaced up to a minus sign by a convex risk measure. And then the representation of the convex risk measure gives you this form. So you compute expected utilities, but under various measures. You take them more or less seriously as specified by the penalty function. And the convexity of the risk measure reflects model uncertainty aversion. It's one of the axioms in the list of preferences. While concavity of U, of course, that's the classical risk aversion. But this convexity is a different thing, different level, model uncertainty aversion. So that takes care of Ellsberg paradox and various other things in this literature on preferences. And convex risk measures come in canonically here at this crucial point. Now, the mathematics of monetary risk measures is on strictly mathematical grounds. A lot of interesting questions, so has been an active research area. For example, you could take the very classical problem of optimal portfolio choice in the following formulation. You want to find the best portfolio under financial and under risk constraints. Now, the financial constraints of affordability can be typically expressed in terms of the equivalent martingale measures. But risk, of course, now risk measures come in naturally, but also best means preferences. So you can take classically expected utility, but in the light of this recent development, it's natural also to bring in risk measures here at this level of the preferences. So mathematically, it involves new projection theorems from the class of measures which appear here in the risk measure at the level of preferences to the class of equivalent martingale measures, which mathematically means you have to extend classical projection theorems by Chisar and others, for example, in discussing relative entropy, divergence measures. Now, from one measure and a class of measures to two classes of measures, and so there are many interesting details which can be settled. Now, a very different and much wider perspective, of course, is what is going on now here in this semester on systemic risk, mathematical modeling, and interdisciplinary approaches. Now, I'm here just to learn, because I had not really thought much about this issue. And this is clearly an interdisciplinary challenge, and this period really takes up this challenge in a very impressive way. If you look at the programs of the workshop, it's really a very broad range of different backgrounds, different perspectives on this crucial issue of systemic risk. Now we have, of course, risk measures now just one element in a much more complex picture, have already turned up at many places. For example, here this work of Chen, Yangar, Moilemi on the axiomatic approach to systemic risk involves a decomposition theorem where you characterize a certain class of global risk measures by a decomposition that they consist in a risk measure of the type we have just discussed, applied to real valued random variable, and to an aggregation mechanism which produces a monetary outcome out of a very complex network picture. So mathematically, that's a very interesting decomposition theorem. Of course, in financial and real world terms, the whole question is, okay, how do you flesh it out? How does the aggregation work actually in economic and financial terms? Then there was this paper by in the lecture of Patrick Cheridito, his paper together with Brunnemeyer on measuring and allocating systemic risk, where also some kind of, which fits into this framework. So they described a specific way of aggregating, and then they applied a risk measure of the type we discussed, specifically utility-based risk measure to the result of that aggregation mechanism. Yeah, I myself last week gave 2 talks on something I find interesting without claiming any relevance so far, namely the interplay if you think of a large network between local conditional risk assessment in terms of risk measures at the nodes of a network and the global risk assessment for the whole thing. What happens if you insist on consistency, and what can you say? And to me, I found that interesting because at some point I worked on Gibbs measures in statistical mechanics, where you specify probability measures on the large product space, describing the configurations in a large network by fixing local conditional probability measures. And then the question is, okay, what can you conclude on the structure of the global random fields, the global probability measures consistent with these given conditional probabilities, which usually are written down in terms of an interaction potential. And this here is kind of the way I looked at it. It's a nonlinear analogy where probabilities are replaced by risk measures both locally and globally. Okay, just one example of many open questions, even in a strictly mathematical sense. And the main point I want to make is that Knightian uncertainty to me is a rich source of new mathematical and even probabilistic problems, and no reason at all to throw the towel, as Lord Turner in a way has suggested in the way he formulates it. So, thanks for listening.
Are there any questions?
Just a thought. I mean, when I sort of try and address some of these issues in practice, I mean, I always take a Bayesian point of view.
Yeah.
So, I mean, this allows for multiple possible modelling explanations of the data that we're seeing.
Yeah.
But it treats them always in a completely consistent fashion.
Yeah.
I mean, one of the things I find more difficult about, say, extremal choices is that they are extremal.
Yeah.
So I find Bayesian methods very effective.
No,
practically.
perfectly okay. My own feeling is that that's certainly one important component of whatever can be done reasonably. But it's not yet the full story, because it seems to me one should also, in this risk measure stuff, combine it really with the idea of stress testing, in the sense that one does some brainstorming and thinks of things which have never been observed so far, but which might so a combination of many things. And what I like about the framework, the conceptual framework, is that it leaves room for a lot of things. Now, of course, the art will consist in fleshing it out in a reasonable way, and there certainly Bayesian technology should play an important role.
There's more than one model of Knightian uncertainty too. You don't need these extremal things to do that. I like a lot the models of Truman-Bewley. And in those models, basically you say there's a big set of probability measures, and you're not really sure which one is the correct one. And if you have a choice which is undominated for one of those probability measures, then it's undominated. So you end up with an incomplete preference ordering. And so when I look at my if I look at my allocation for my retirement money in stocks and bonds, I certainly don't want a target date plan which has no science behind it. But if I think, what's the fraction that I'm going to put in stocks and what's the fraction I'm going to put in bonds, I don't really know what my preference parameter is. Well, that's a whole other thing. That's
Right.
But let's say that I know my preference parameter, I can come up with some number for that, and I still don't really know what I think the expected return on the market should be. And if I look at the portfolio choice there, and I'm going, yeah, that backs. If I look at if I currently have 60% in equities, if I back out the expected return that comes from that, it's not a crazy number, then that's within the set of probability assessments that I think this is an undominated choice, and I'm happy with it.
Yeah.
So I think there, you know, I think that there are some interesting things there, and I think that there's certainly things that people do where they don't switch very quickly, and it looks like they're inconsistent. They can be explained by that.
Yeah, okay. No. Yeah, as I remember, Trumbull also had a way of redoing large chapters of general equilibrium theory in terms of this model ambiguity, which looked very, very interesting. A little bit similar in spirit as this recent outburst of redoing the fundamental theorem of asset pricing without probability.
Any other questions? Thank you very much.
Okay.